The broadcast is now starting. All attendees are in listen-only mode.
Okay.
My name is Paolo Frankel. I'm the head of the Renewable Energy Division at the International Energy Agency, and it is my honor and great pleasure to welcome you all at this webinar on next steps for energy systems integration. First of all, I would like to say I hope that anywhere you are, you, your families, your friends are all safe in this incredible and special crisis moment. But it's important to go ahead. I just read an interesting article in the Financial Times this morning reminding that the climate change crisis will remain with us and we have to continue to work. So it's a pleasure indeed to organize this webinar together with Agora Energiewende. It's a pleasure to see colleagues of Agora, Frank Peter, and also many attendants. Attendants now are reaching 300 people right now, and there are more than 500 registered. So thank you very much for your interest. This webinar is part of a series of events organized in the framework of the Clean Energy Ministerial Power System Flexibility Campaign, an effort which is led by China, Denmark, Germany, and Sweden, and where we have been working for the last 2 years on 3 main areas: on digitalization, on market design, and energy systems integration, with emphasis on transport electrification, which is the subject of today's webinar in particular. Now, at the IEA, we are, and we were already before the crisis explosion, looking at 2020 as the year of clear energy transitions, which calls for a reinforced work looking in particular at the decarbonization of hard to tackle, hard to abate sectors like transport and also energy intensive industry. Now, these calls for an attention in particular of electrification of end users, but also on the use of hydrogen, which is the main goal of today's webinar. Now, even before the crisis, we passed the narrative to work together, and the IEA called for a grand coalition of willing to make sure that 2019 will be remembered as the peak year of emissions, and this not just because of the economic crisis, but for more structural and good reasons in the future. Now, looking at electrification and hydrogen, it is very important that all this happens in an environment which ensures security of supply at all times. Electricity security in particular becomes very, very important. And think just 1 second what would happen now in this crisis context if we had the problem of electricity supply. We would not have IT connections, we would not have hospitals working. It would be absolutely much worse than ever. So this is why the topic of the webinar today, which is looking at some specific cases for energy systems integration and innovative ways to use electricity and hydrogen for the decarbonization, is so much important. During the webinar, we hope to exchange experiences on concrete steps that can be taken to accelerate the uptake of electric mobility and to assess the short to mid-term potential of hydrogen in clean energy transitions. And I believe that identifying actionable priorities is key, in particular in this moment, where a number of governments are also considering to look and to include decarbonization and sustainability aspects in the stimulus packages that are being prepared around the world in response to the COVID-19 economic crisis. I would like to say that IEA is standing ready to support our countries on this, and we of course are very, very happy to work with stakeholders, with Agora, but also all our PSF partners in this respect. And in the coming weeks, we will be preparing a series of special policy briefings and communication to reinforce our support to our member and association countries. This has already started. If any one of you has been recently on our IEA website. Now, without further taking time from you, I would like to wish you a productive meeting, and we very much look forward to a dynamic discussion. I give now the floor to Frank Peter for your remarks. Thank you very much for your attention. Thank you.
Thank you, Paolo. Yes, very welcome. Warm welcome also from our side. We are really excited to be part of such a great meeting, great effort. And what we, of course, have to recognize is that current times are overlaid a little by the corona crisis. But as we experience, the machinery rooms in the policy environment are still working on the topics of energy transition. Now they, of course, have to come in a little other light. Corona crisis is also tackling energy transition policies, but nevertheless, still the topic is there, and we want to make progress for in the specific areas we want to tackle today as well. My name is Frank Peter. I work for Agora since now exactly 3 years. And I'm the deputy executive director and the research coordinator of our organization. And I will be responsible for moderating the second part of this webinar. Just one technical remark: if you have questions on the speakers, please present them in the chat. Farah will collect them in the back and give us to the moderators or give themselves into the discussion. And whatever question cannot be addressed for timely reasons during the webinar, please feel comfortable to also contact the speakers afterwards via mail to address your questions. That should it be. So please, Enrique, I guess you're the next speaker in line, then go ahead.
Hi, yes, good morning to everyone. Thank you both, Paolo and Peter, for your words opening the session. Also, thank you, Peter, for giving the first few kind of housekeeping questions. So, yes, please send us all your questions. Also wanted to remind you, following the reminder yesterday, that we will be recording the session to both replay and disseminate further after this event. So it will be available online. Please let us know if you disagree with this, and we can see we can take the necessary measures to handle your personal information in this regard. Other than that, we look forward to your questions, and I'm going to get started with my presentation. My name is Enrique Gutierrez. I'm working with the IEA also for 3 years now, and today I'm presenting this event as part of the Power System Flexibility campaign. First, I'd like to tell you a little bit more about, if we can move to the next slide, about the IEA's activities in this area, both on electricity and energy systems integration. We have been working in this field for a number of years now, and through a number of publications on status of power system transformation or country-based analyses looking at specific power system transformation scenarios for countries based on requests from our member association countries. And overall, we also have topical and special reports. Most importantly, the World Energy Outlook from 2018 had a special electricity focus. And there's other publications more targeted, for example, the future of cooling, the Global Electric Vehicle Outlook, and also the market report on energy efficiency and renewables, which we'll also be referring to throughout the slide. Moving on to the next slide, a little bit, I think Paolo already spoke about the System Flexibility Campaign, which is a clean energy and ministerial initiative. And as you can see, we have a strong base of country members from around the world, with great colleagues, China, Denmark, Germany, and Sweden. And also one of the strengths of this campaign, I think, particularly thanking Agora and Agora for the excellent collaboration in putting this event, we had a very active base of members, both from private industry, from private sector, think tanks, non-governmental organizations, system operators, manufacturers, and so on. And that really helps us put together the most innovative practice in terms of technology, and also identifying what the policy priorities are actionable in the short term for policymakers now. Now moving on to basically what brings us together today. As Paolo mentioned today, just now, it's important to make sure that 2019 is not just, an anomaly in terms of emissions, and really make it a peak. Now, if we look at current trends, our emissions are set to grow on a yearly 1% until 2050, which basically continues the trend of emissions we've been seeing since 2010. Now, if we consider the current stated policies that we have in the countries around the world, we see that the emissions trend goes down. If we could have one more click, please. The emission trends go down comparatively to where we're going now, but it's still not really where we want to go. Now, if we can show the next click, this is really where we want to get. If we're far from really reaching our targets in terms of international climate targets of air pollution and access, and that's the reason why the IEA has been carrying out country-by-country analysis of pathways that could lead to meeting these targets based on each country's specific policy preferences, resource availability, and societal preferences. Of course, this needs stronger action in 3 key areas. These areas are energy efficiency, renewables, and also fuel switching, including CCUS and other fuels. And this kind of relating to the title of the slide, there's no single or simple solutions, but there are areas we can work kind of in a targeted manner. And if you look at the graph in the green area, you can see a visible contribution of renewables, wind, solar, biofuels, other renewables. And underneath it, you also look at significant contribution of the value of fuel switching, of electric vehicles, and of course, this energy efficiency that helps to this. And if we really are serious about meeting these targets, then it's important to accelerate the deployment of such important solutions to make a significant contribution. Particularly of fuel switching, and moving on to the next slide, it's a question of, okay, so what is the impact of shifting this energy demand and electrifying it? I think there's 2 key trends in electrification of demand. One of them came up in the recent Future of Cooling report that we published, is the increasing demand of space cooling and how it will drive electricity demand. So this graph shows that basically between 2016 and 2050, electricity demand is expected to almost triple, driven by space cooling, and much of this by residential. If we continue as we are currently, this leads to, if we go back to the slide, this leads to electricity demand of about 6,200 terawatt hours, which is roughly equivalent to China's electricity consumption in 2017, just to give you an idea of the magnitude of the electricity demand. Of course, and it should be said that this is assuming an efficient space cooling. If we take actions now to improve the efficiency of this space cooling, we can reduce this demand to about 3,400 terawatt hours, so it's almost halving the energy consumption. So it is a challenge, but it's also an opportunity. And then moving on to the next slide, it is an opportunity, particularly when pairing different resources. For example, one of the analyses that we made in this report was looking at a case study of India and the power system in 2050 that has very ambitious renewable deployment goals. And it expects, for example, having a PV deployment of about 1,000 gigawatts in 2050. What this leaves, the challenge here is, of course, that there's a significant increase in electricity demand due to space cooling and giving a system peak around 7 p.m., but also a significant surplus of solar energy around noon. If you look on the left-hand side, you have both the peak about 7, this black dotted line, and also the solar curtailment, which is a non-shaded solar yellow part during noon. One of the analyses we made for this report is the importance of load shifting to actually make the most out of the surplus renewables, to also reduce the peak in the system, and using a combination of measures including thermal storage and district cooling to an equivalent of about 178 gigawatts with 3.5 hours duration of storage. We were able to basically shift the surplus solar to the evening peak, and thereby reducing the evening peak by 11%, or roughly equivalent to 80 gigawatts. So there's still, if you take concrete action now, also there is potential to kind of and identify synergies between increasing demand and increasing penetration of renewables. Of course, there's just one trend in electrification. Now, looking at transport electrification, if we can move to the next slide. These are some figures of deployment of EVs based out of the Global Electric Vehicles Outlook, which project 2 scenarios. One of them is the new policy scenario, basically expecting that by 2030, deployment of EVs will be just around 135 million vehicles around the world. And with the EV 30 by 30 scenario, we expect around, so roughly 250 million electric vehicles deployed around the world. This comes, of course, with shifting, particularly in fuel switching, but also with an increase in electric demand. And in the new policy scenario, this is 640 terawatts by 2030 of additional electricity demand. If you consider today countries like France or Germany, the demand is roughly under this 600 terawatts, so it gives an idea of the scale. And if you look at a full, more ambitious scenario of EV 30 by 30, the electricity demand reaches 1,100 terawatt hours, which is roughly equivalent to, say, India's electricity consumption nowadays, previous year. So, I mean, it seems like a huge increase in demand, but also bearing in mind that this 1,100 terawatt hours is about a third of the inefficient scenario for electricity demand due to space cooling. So it's, of course, not significant, but still has an impact on the power system. And another good news is that a significant amount of this electricity demand is expected to be provided by slow chargers, which, as you will see later on, they provide the greatest flexibility to the power system. So there is a space for opportunity. Moving on to the next slide, and one area where we have identified this potential is in a study we did, an analysis we did for the China Power System Transformation Report, where we modeled the power system in China in 2035 according to the Sustainable Development Scenario. And here you can see it's also the potential of optimizing EV charging to reduce peaks and increase renewables penetration. Basically, here I have two sample weeks, one with minimum net load and the other with peak net load. And you can see the difference between the original net load, which is on the blue dotted line, and and the difference with the green continuous line, which is the net load with smart EV charging. In both cases, you see that it contributes to a reduction of the ramping requirements. It also contributes to better operation of the thermal plants that have run into less minimum load constraints. And particularly, one of the significant findings is that fully optimized smart charging leads to a 14% reduction of the original load, which translates into about 165 gigawatts. Of course, this has to be said, this is a modeling exercise where this is an upper end to the total flexibility you can get, as you're assuming that the full fleet of electric cars in this scenario is being used to in an optimal way to balance the load. And of course, to really make the most out of this potential, you really need intersectoral policy coordination, both on the transport side, power system, retail rates, and other bits we'll see later. Of course, moving on to the next slide, so far we have only seen the system-wide impact. And something that we're finding with the deployment of EVs and other distributed energy resources is that the greatest impact is felt at the distribution level. On the left-hand side, you can see a graph from the German Ministry of Energy and Economic Affairs, where you see the great investments in Germany between 2010 and 2018 and how they've increased significantly. They increased from 2016 onwards compared to 2010. But most importantly is that in all cases, the greatest amount of investment has been going to the upper half, which is the distribution networks. In 2018 alone, this amounted to around 6.4 billion euros of investment in network capacity. Now, of course, this is until today considering only the deployment of distributed energy resources and solar PV. The question is what happens in the future as we have more EVs and more distributed batteries and more PV being deployed. A recent study commissioned by distribution network operators in Germany found that from now to 2035, if we continue planning the networks as we do now and assuming the current operation patterns that we have now, this would come about with a total investment required of about 36.8 billion euros. Now, if instead of doing that and you account for flexibility in the future planning of your investment requirement, this total investment requirement could be reduced to about 19.8 billion euros. So this is roughly a 55% reduction in total investment requirements. And if you break down this to yearly terms, and already, as you can see on the right-hand side, you have a bill that is planned, but you also have an ideal case where you account for flexibility. If you even account for the deployment cost of flexibility, you can reduce the investment requirement by about 44%. Of course, this needs to change the way we plan our networks in the future and the way we recognize the flexibility options in the regulation of network businesses around the world, of course. Moving to the second slide. Of course, one thing to really, so far these to really understand the impact that transport electrification will have on the power system, it's also important to understand that not all mobility needs are the same. This means, for example, the type of the charging type, the charging time, the utilization will depend a lot on the type of mobility service that you're providing. So, for example, a small private car that can charge either at home or at your workplace won't have the same charging flexibility as, say, for example, a public transport electrified fleet that charges in the depot at night and ensuring that it has like the whole charge throughout this charging session. Or, for example, mobility fleets such as ride-hailing apps, where they need to charge constantly throughout the day and have a very, very high consumption and very frequent charging sessions. And making sense of all these different charging profiles of, for example, service fleets gives you an idea of what will be the charging infrastructure requirement, and really planning ahead to have sufficient and publicly accessible charging infrastructure. So that's kind of the scale of the challenge, so to speak. But that's something that we'll learn about in the next couple of presentations. Then moving on to the next slide, please. Of course, the choice of charging strategy matters. I guess the easiest thing is not doing anything and letting unmanaged charging. So, for example, this would be just providing no signal to consumers to charge a car whenever they want at the time they want, which is of course possible, but of course comes with a significant requirement for investing in additional generation and network capacity. A second step to improve this would be introducing smart charging through implicit signals, for example, time of use pricing, which basically you can provide a signal to consumers to charge at a time when it's cheaper and better for the system. In terms of technical requirements, this comes with the necessary IT systems and the control to manage the charging speed. But also in the policy arena, it requires the introduction of time of use tariffs to manage this charging. On a third level, which is probably better, the problem with it's aggregated smart charging, which of course has a technical requirement of having greater IT control and greater monitoring in order to enable third-party providers or retailers to offer the consumers a package or a service where they can assure them that the mobility and charging requirements will be assured, but also aggregating their charging flexibility to offer to, for example, centralized ancillary service markets. Of course, this requires on the policy side, enabling access to aggregators and also to aggregating loads to really participate in market services that have typically been designed with big conventional thermal assets in mind. At a fourth level, there's of course the coordination of large-scale, wide-scale, both bidirectional charging and smart charging. The difference between smart charging as unidirectional charging and V2G is that one involves only adjusting the speed of charging for a car, but once your car is fully charged, you can't really discharge. And with V2G, you can both discharge and charge throughout the charging session. So if you think the 8 hours that a car would sit idly at home, it allows for an increased use of flexibility, and some studies estimate around 7 to 13% more energy value when you have V2G. Of course, it comes at a higher cost proposition than current smart charging technologies. So, of course, the technical requirement is having the availability of the V2G technology at scale to really rely on it. And on the policy side is having similar to smart charging, is having the ability to aggregate loads, but also, for example, pushing for manufacturers to really bring the scale to the economies of scale in terms of manufacturing deployment, or and also quite importantly is addressing tax and levy issues that might lead to double charging, as you have with, for example, stationary batteries. In the end, the long-term impact or contribution of electrifying mobility will depend on the policy choices today. And I think my last, moving on to the next slide, of course, this comes to the question of where is the flexibility of EVs being deployed today. And we see it around the world in a number of very different cases. Is it either through retail companies going into arbitrage in the wholesale market, doing load reduction programs? One very typical case in Europe has, for example, the participation in ancillary services such as frequency response, but also increasingly the services being run by distribution system operators such as non-wire alternative programs, congestion management, or local ancillary services. And the good thing about having a diversified set of market opportunities for EVs and other distributed energy resources is that it allows to uncover the areas where EVs really bring value to the system in a cost-effective manner, and actually contribute to overall, in the end, reducing the cost of operating the system and resulting benefits to the end consumers. Just to wrap, I think my 5 key takeaways that I'm happy to discuss throughout the session today is that 1, there are different pathways for transport electrification. 2, that local distribution systems are likely to face the greatest burden of EV integration. That there's a need for a coordinated approach between charging infrastructure deployment and network development. That the synergies between EV deployment and VW integration need to be assessed in light of the fact that mobility services will have priority over power system needs. And the last one is that to really make the most of these system benefits, it's important to coordinate between a broader array of stakeholders, such as car manufacturers, transport planners, power system planners, industry, and so on. I thank you very much, and I yield the floor to the next presenter, Mr. Der Sayed, to deliver his presentation. Thank you very much.
Thank you very much, Enrique. My name is Der Sayed, and I'm the director of Shura Energy Transition Center, a think tank which is the first and the only think tank of Turkey working on energy transition issues. And I'll be sharing some insights from a case study we carried out for the case of Turkey, which is one of the largest producers and exporters of vehicles in Europe. However, in terms of electric vehicles, especially the passenger vehicles, it's starting from a very low base of development. So an important question which the Ministry of Energy and Natural Resources is trying to understand how the integration of higher shares of passenger vehicles in Turkey in the coming years could impact the distribution grid. And we released this study by end of 2019, which was also the time when the local car producer in Turkey has released the plan to produce Turkey's domestic EV in the coming years. So there's a big expectation of a rollout of many electric vehicles starting in the next 2-3 years. So it's an important question that needs to be addressed. Next slide, please. If you could just scroll down until the end on the key findings from the study is we've investigated in principle 2 distinct market scenarios until 2030, so until the next 10 years, where 2.5 million and 1 million EVs, battery and plug-in electric vehicles are taking part in the vehicle stock. So that represents around, so the high end of this scenario range represents 10% of the total vehicle stock. By 2030, implying 1 out of 2 cars sold are electric vehicles. To be able to charge these EVs, we looked into 1 million charging points by 2030 at 3 different places, basically home-based, workplaces, and also public available areas. And we used real distribution grid data, which makes the study quite an interesting one, which represents 4 largely populated and high economic activity regions of Turkey: Aegean region, Central Anatolia, Marmara, and Mediterranean regions, which are also the regions where much of the markets are expected to be developed. The main assumption here, without EV electricity load, that the grid demand will increase by 5% per year between 2018 and 2030. And on top of that, there would be additional EV load. To be able to meet the 5% electricity load, we modeled the distribution grid investments accordingly. And then we investigated where additional EV load can be integrated into this system. Of course, there were further assumptions in the analysis, besides the grid investments continuation, smart charging mechanisms I'll tell a bit later what I mean with that for the case of Turkey. And electricity tariff structure would be improving accordingly to manage peak load hours. And if all these market design and investment angles of power system continue, then the 2.5 million EV scenario could be integrated by 2030 with minimal additional investments in the distribution grid. And here, renewable energy, especially distributed generation and storage, plays a key role to minimize impacts, especially during summer days. Next slide, please. If you look at the case of Turkey, transport sector represents around a quarter of the total demand, and in terms of emissions, depending on the year, is either second or third following electricity sector, because nearly all transport sector emission energy demand is sourced from fossil fuels. As I mentioned, the share of EVs is quite low, 1,500 EVs out of 12.5 million passenger vehicle stock in Turkey. Next slide, please. And within the G20, Turkey has per capita transport emissions relatively low compared to rest of the G20 countries. However, in terms of the growth in percent in the past 25 years, it ranks fourth after China, Indonesia, India, and Turkey. So from an emission perspective, it's a rapidly growing country, which will eventually reach other G20 country levels in the coming years. Next slide, please. In the scope of the study, as I mentioned, two scenarios have been investigated. Only passenger electric vehicles have been looked into. We looked into also 4 metropole and 4 rural regions within 4 distribution grids. So as you can imagine, each distribution is quite different in terms of characteristic structure. So we chose, and I'll tell you a bit later about that, quite different grid examples for this study. And for each pilot region within these grids, we looked into different EV driving charging behavior possibilities, as well as different charging points, technology type, and locations. We connected this distribution grid modeling with a GIS-based modeling also to place the charging points in different locations. I'll give some examples of that. Eventually, we have had 16 million scenarios in this analysis because of all these different probabilities, and we boiled that down to 16 scenarios at the end for 4 seasons and 4 full days within each season, and split into metropole and rural regions. And we looked into overloading, voltage violation, capacity factor of distribution grids, and additional investment needs to see how 2.5 million EVs can be integrated to Turkey's grid. Next slide, please. As I mentioned, a load growth without EV load of 5% per year have been assumed, and accordingly, it has been assumed under a reference case or a reference model that investments will take place in the distribution grids until 2030. And I must also say that our modeling capacity allows for hourly resolution model for all years until 2030, which is quite a powerful aspect of our analysis. Next slide, please. A few words on the EV sales. As I mentioned, Turkey starts from a low base, but we assume that the total growth will be quite rapid once the domestic EV is in place to reach 1 out of 2 cars will be EV or plug-in hybrid EV by 2030, and representing 10% of the total vehicle stock by 2030 that you see on the left-hand side. Next slide, please. We evaluated 5 different points of charging: AC1, AC2 at home, AC2 at work, and in public places, including 1 fast charger at 100 kilowatts capacity, and AC2 as well for public places. And on the right-hand side, you see for the high growth scenario that there's 1 million charging points placed across different parts of Turkey. And I'll give you an example now on how it looks like at the city level. Next slide, please. But before doing that, the 4 distribution grid areas we looked into are from Ankara, from the Mediterranean region, Istanbul, and Izmir, 1 urban and 1 rural area. And this 4 grids represent 1/3 of the total population and the electricity demand. and there's a good sample of different type of subscribers in each distribution grid, including residential, commercial, industrial, and irrigation consumers. So we have a good sample of subscribers to be able to draw global conclusions for the entire Turkey. Next slide, please. What we did, and this is from the example of Istanbul, was to place the charging points in each region we looked into. So the GS here represents the gas stations, and we placed public charging points in different gas stations. There are two shopping malls in Kartal, Istanbul region. This is one example only, as you can imagine. East Marina and No Marina, one on the left and one on the right-hand side. These are the public charging points or working charging options, and each one of the red dots actually represents a consumption point in the grid, and we group them to be able to make an assumption for home charging points, and that was the third level we evaluated, and we did this type of analysis for 8 regions we looked into in this analysis. Next slide. And as you can imagine, there is quite a large probability in when the drivers will come home and to be able to start their charging, and we have developed probability distribution function for all charging points, and also made some assumptions on the state of charge, where we assumed the peak will be when people decide to charge when the battery is 20% full. So all these different combinations eventually result in 16 million scenarios, and we made selections out of these 16 million scenarios for seasons and days, and for all different grids to have representative samples for each grid model we had. Please, next slide. Now, one last point on the methodology. We have evaluated 2 types of charging support. One is more charging on the public areas, which eventually leads during the day a peak at the DC level, which you see on the top of the slide. Shaded blue bars, and then we have the home-based charging support, which takes place during the times when people sleep. That's on the left-hand side. That's with more red and green bars. And we wanted to see how different electricity tariff structure and smart charging mechanisms could have impact on the charging and grid integration. Now let's look at the results a little bit. Next slide, please. We've tested the impact of EV integration on the number of problems at the low voltage and medium voltage distribution grid. So number of problems on overloading, number of problems on voltage violation. And you see that, for instance, in Kartal, which is the urban area of Istanbul on the Anatolian side or Asian side, there have been 6 problems when there's public home-based charging, and less when there is home-based charging support. And in Şile, which is a relative rural area in Istanbul, there's also several problems. Different problems in different regions. There is no consistent output, but to give a perspective on the number of problems, this is quite a limited number of problems throughout the year one distribution grid could face. So it's actually quite a reasonable and a positive outcome from the perspective of EV integration. And I'll show a bit on the investment side. Next slide, please. In terms of the investments, we looked into the transformer capacity and the distribution line. The blue shaded bars represent the current situation. The green shaded bar is the reference model. So what will happen without EVs, with a 5% growth, how much investment is needed. And the EV integration is represented by the very little orange bars, and that's just 1 to 10% of the investments that are planned in the green part. So it's quite negligible, and also quite, again, a positive outcome from the impact of EV analysis. Next slide, please. And I think this is important for the charging infrastructure investors. Here is the capacity factors of the different charging points. So basically, at the DC level, the charging point capacity factors are between 5 to 10%, so relatively low, which is also a typical outcome of countries which start from a low base of EV deployment. So there may be some support needed, but on the other hand, for other charging points, it's quite okay. Next slide, please. And we did a sensitivity analysis to reduce the electricity load from 5 to 3%, so less investments. We grouped the charging stations. We looked into also renewable and storage integration. And if you look into the next slide, I'll try to go, be a bit quicker here to summarize. Basically, when the demand growth decreases, so there's less investment in the distribution grid, basically on the bottom you see that the problem number increases by basically doubles. What one favorable outcome was, if you are to have less charging stations at public places and you place them more strategically, it also implies that the charging is done more efficiently and more optimally, so that reduces the problems from 6 to 4. I can go deeper into these results if you have questions, and maybe the next one, and then the next one, please. So let's look at the final results and key takeaways. The next one. To conclude, if you can just click on all of them. So from this analysis, we were able to draw 7 priority areas for deployment in Turkey, for primarily for the Ministry of Energy and Natural Resources, but also other public institutions. There's a need to accelerate the market for EVs and charging services in parallel. Smart charging mechanisms, especially home-based charging mechanism in the case of the study for load management was quite favorable. There is no single region where same measure applies to solve the problem number, so there are region-specific measures needed. Different business models will need to be developed for both the charging infrastructure companies, but also for the distribution grids, utilities. There is a must need to continue the planned investments in distribution grid in line with the growth in electricity demand. There is a clear synergy which needs to be utilized between renewable energy, energy storage, EV charging. And from a national perspective, if Turkey wants to domestically produce its EV, the benefits of this need to be hand in hand assessed. So that's all from the case of Turkey on EV integration. Thank you very much.
Thank you very much there. That's certainly a very interesting analysis, and looking forward to discuss it at the end of the presentations. Now I'm going to hand over to Urs Meier from Agora Verkehrswende, who will tell us a little bit about the recent study they carried on distribution grid planning.
Yeah, hello. It's great to be part of this webinar. Many thanks to the organizers. I can't see my presentation on the screen yet. I suppose it's, yeah. So I can already start. Yeah, so hello again. I'm Urs Meier, Senior Associate Energy and Infrastructure at Agora Verkehrswende, which translates Agora Transport Transformation. We see electromobility as key to an energy transition in transport. And one argument we had been confronted with quite often was simultaneous charging of electric vehicles will lead to either electricity blackouts or unreasonable grid expansion costs for the society. That's why we started this study, whose main results I'm going to present to you today. We, that is my colleagues Stephanie, Andreas and Frank from Agora Energiewende and the Regulatory Assistance Project. So next slide, please. The contractors were Navigant, Kompetenzzentrum Elektromobilität, Infrastruktur und Netze, as well as Re-Expertise. So those researchers did the modeling and the research, and the organizations being involved in the concept. I already mentioned RAP, Agora Energiewende, and Agora Verkehrswende. The research questions were, first, what investments in power lines and transformers on low voltage and medium voltage networks are needed to further the energy transition in the areas of electricity, heat, and transport? Why are we looking at those 3 areas? because we think that you cannot separate them, and it's not possible to determine which cost driver requires how much network expansion, because they are intertwined. So although electrification of transport was the focus of this research project, all of the findings about investment requirements apply to all three drivers. That is very important. The second one, to what extent does grid-friendly charging of electric vehicles reduce the need for network expansion and the associated investments? And by grid-friendly charging, I mean charging that reduces the peak loads created when vehicles and electric heat pumps are charged simultaneously. It can also shift electricity consumption to times with abundant generation from solar photovoltaics and wind turbines. The third question, what effects does the mobility transition from private cars to public transport, cycling, walking, and shared mobility options have on grid expansion investments? We see that in many studies we evaluated, we saw this change of the mobility system was not mentioned, and it was a continuation of the current transport system. And, especially with respect to shared mobility options, ride sharing, etc., it is important to have assumptions for that as well. And the fourth question, what regulatory framework is needed for charging electric vehicles to really get such a smart charging environment? You can download the study in German, and you can also download conclusions in English from our website. Next slide, please. So let's have a look at the scenarios. As I said, we can't separate the three sectors, but I will focus on the transport sector. We have a scenario or two scenarios for the year 2030, or for the years up to 2030. 6 million vehicles, battery electric vehicles in scenario F1. 15 million in scenario F2, that is the market ramp up. The government's target is 7 to 10 million electric vehicles. So we wanted to know what even a very quick market ramp up would look like in grid expansion investments. And you see the assumptions as to PV and wind onshore below that, and also to electric heat pumps. For the year 2050, we then have two scenarios. One where we have a continuation of today's transport system, 45 million battery electric vehicles, which represent the full fleet of cars in Germany, which is currently at 47 million or so. And the other scenario, M1, having 30 million battery electric vehicles, which then also represents the full fleet of cars in Germany. You can't see here in this slide that we also have 90,000 buses included in the modeling. What we don't have is the freight transport. So this whole study modeled passenger transport on streets. Next slide, please. So let's see what smart charging actually reduces the investments in distribution grids. It is up to 50%. You can see that on the right-hand side in the scenario F2 with 15 million battery electric vehicles, which is then quite some reduction. And you must know that this is the outcome of a model, and we of course had to define smart charging. This type of simple smart charging means that you can shift the time of charging within one time span period of parking the car. So if you come home from work at 6 o'clock in the afternoon, you plug your vehicle to the wall box, and the model says that you need to recharge all the energy you used up on your last drive. And the problem then, of course, is if you at 7 o'clock after 1 hour or so go to the gym or whatever, take the car, then there is no time for shifting the charging process. So it's smart charging, but it's limited. So that's why we looked at Smart Charging Plus. Next slide, please. Smart Charging Plus means that we can shift the charging process beyond one parking time. This is what in real life you would actually do. You wouldn't plug in your car for a 1 hour stay at home where you know that you need to take the car again for a short ride. So Smart Charging Plus in the model means that we allowed the model to cut 3% of the delivered energy over 1 year. That would be then the demand peaks, the load peaks. And of course, this would mean a reduction of comfort for the EV driver, which we don't want to have. So I will talk about that a bit later when I talk about the regulatory measures that should be taken in order to have no comfort reduction for the users. So we think it's possible to have this Smart Charging Plus without any customers or EV users actually realizing a reduction in comfort. Next slide, please. So is this then going to be more expensive, those investments in grids than what we did in the past? No, we say on average future EV grid integration does not require more investment in cables and transformers than in the past. On your left-hand side, you see the 4 scenarios from our study. Please focus on F3 and M1. And on the right-hand side, you see the investments in the distribution grid over the last 10 years. It is important to note that the figure compares between investments in low and medium voltage grids on the left and investments in low, medium and high voltage grids on the right. We didn't get the data to separate that. So if you want to fill that gap, you can say the investment requirement at the high voltage level up to 2050 can be estimated on the basis of literature at around 60 billion euro or 1.7 billion euro per year. And if you add that 1.7 billion to the 2.1 billion in scenario F1, you get to the 3.8. So we say on average, it is not more that needs to be invested than in the past. Next slide, please. The next thing we say is electromobility finances the expansion of the distribution grid until 2050. To be more precise, electromobility can fully finance the expansion of the distribution grid in terms of lines and transformers. I'm not referring to information and communication technologies, the smartness actually, for the electricity, the heat, and the transport sector in Germany until 2050. So how do we explain that? We have 45 million electric cars in 2050, and they increase the electricity sales by around 120 terawatt hours. Today's grid charges are around 7 cents per kilowatt hours. And if you reduce that 7 cents to 4 cents per kilowatt hour by 2050, that those 45 million electric cars would bring in up to 75 billion euros, and those 75 billion euros would be needed for the scenario 45 million electric cars with Smart Charging Plus. So it's a continuation of the current transport system, but it's with Smart Charging Plus. Of course, the final contribution of electromobility must be determined politically, which brings me to the next slide, please. The goals of smart regulation for grid expansion and for smart charging. Obviously, we need adequate financial contribution of electromobility through grid charges and maybe construction cost subsidies. Smart charging need to be standard, so we need comprehensive controllability of electric cars through financial incentives. if possible, and if that's not incentive enough, maybe even obligations. So really, we need that controllability of electric cars, but not in general terms. Of course, we need rapid distribution of information and communication technology for forecasting and control. But, and this is very important, we need a priority of preventive indirect control. So time of use tariffs for grid charges or maximum timetables, anything that allows the user to use and to choose a charging system that that fits his or her needs, and it does not include a cut of electricity demand or supply when you really need it. So direct control of distribution grid operators should only be the ultima ratio. Next slide, please. I'll get to the main results of our study and my presentation. First, the energy transition and the power distribution grids can be successful, even if all passenger vehicles are electrified. Grid-friendly charging reduces the peak loads created when vehicles and electric heat pumps are charged simultaneously. It can also shift electricity consumption to consumers, consumption to times with abundant generation from solar photovoltaics and wind turbines. And second, combining grid-friendly charging with the broader mobility transition can fund the energy transition in the electricity distribution grids by 2050, supplying 1.5 billion euros of annual investment in power lines and transformers. Without this mobility transition, the annual investments would be 2.1 billion euros. And we would have then those 45 million cars instead of 30 million. Next slide, please. So I also explained that electromobility can finance the expansion of the distribution network until 2050 in Germany. Electric mobility increases the electricity sales, while the overall investment needed for power lines and transformers does not increase. However, it is important that the participants in the mobility transition pay their fair share of grid fees. And last but not least, smart charging can be designed to ensure that users hardly notice any restrictions. To achieve this, grid-friendly managed charging must become the standard. We need secure information and communications technology, incentives, and, if necessary, obligatory managed charging. Precautionary indirect control in the form of incentives for grid-friendly charging should take precedence over direct control by the distribution grid operator. Thank you very much.
Thank you very much, Urs. Definitely a very interesting presentation. I already see a couple of questions for you directly, actually. So we'll take those up after the next speaker, who is Nicole Thompson. Who's going to tell us a little about an optimized Prime project. Very interesting. Also very happy to have you here, Nicole. Welcome.
Great, thank you. First of all, thank you to the IEA for inviting me to speak and everyone who's joined online today. I hope everyone's been keeping safe and well. And my name is Nicole Thompson. I'm the Director of Social Innovation and Head of Co-Creation Partnerships for a global technology and data solutions company, Hitachi Vantara. We can, next slide. So just briefly, Optimized Prime, it's an industry-led innovation and research program that focuses on the electrification of commercial fleets and the impacts it has on electricity distribution networks. So we're doing this through a collaborative ecosystem of partners across the value chain. What makes this project so unique is really it's in its scale and diversity. We're collecting and analyzing data on up to 3,000 commercial EVs across 3 different use cases. These use cases include vehicles that charge at home, so the home-based fleets, as well as vehicles that charge at depots, and also your private hire mobility taxi fleets as well. The key aim of this project really is to speed up the transition to EVs for commercial fleets to help meet our net zero carbon emissions targets, minimize the impact that these vehicles could have on the distribution networks while saving costs for electricity customers. We're also trying to understand what's needed to help businesses overcome the operational, commercial, technical challenges that come with electrification of these vehicles, and then ultimately help the UK plan and prepare for EV mass adoption. And we're going to do this through openly sharing our learnings as well as the data. This is a Ofgem funded project through their network innovation competition. It's about 50% funded through Ofgem, which comes to about 16.4 million. And then the other 50% is also through contributions from the partners. So in total, it's about a value of 35 million. Next slide. So I just want to put this up in terms of why we're doing this project. There's a lot of speculation out there and a lot of, kind of guesses or predictions around what the impact this is going to be. And I think the key message here is there's still a lack of uncertainty and data. So there's different scenarios I've put up in terms of what the national grid think this impact potentially could be. And I know there's been other research, out there done by an example of a capital economics consultancy in London, and their prediction that by 2050 we'll have to invest about 38.5 billion in network infrastructure upgrades. Now this is for both electric vehicles as well as electric heat pumps. But I think again, ultimately, there's that lack of uncertainty and there's a lack of data. Next slide. So from a research perspective, there's really main question that we're trying to answer. One of those is around understanding how do we quantify and minimize the impact of commercial EVs? What's the value proposition for smart solutions for both the fleets as well as the private hire operators? And then also what's required in terms of infrastructure, IT, charging, in order to enable this transition. Next slide. So our approach is, we believe we need to take a whole system view in order to really understand these requirements. And by doing that, we need data, we need collaboration, that cross-industry collaboration from a collaborative ecosystem of partners. We're working with several different partners that I can talk about in a bit, that, from both the energy, the transport mobility, as well as distribution technology, and to be able to openly, make that data available to each other. To be able to address this, we're also utilizing IoT to enable data exchange between siloed areas of activities. IoT also, leads to optimized and automatic decision making, which can result in better benefits or more benefits at a system level than really at the sum of, the savings at each individual level. Next slide. So for our depot-based fleet, we're working with Royal Mail. Royal Mail is the largest commercial fleet operator in the UK. They've got over 46,000 vehicles across 1,700 sites. You can do the next slide. And what this trial is aiming to do is address, several different problems for both the network operators as well as the fleets. And those include, customers over specifying connections and not utilizing network capacity efficiently. They tend to do planning, which tends to be done on a worst case scenario basis. For the depot fleet operators, potential network constraints could result of, them not being able to actually electrify their vehicles in terms of the cost for the infrastructure that's needed for that could cost more than the vehicles themselves. And then also complexity with depot design and planning. So if you think about Royal Mail, they've got 1,700 sites, and, I think originally it took them about 3 years to do 70 vehicles. So if you imagine, with 46,000 vehicles across 1,700 sites, how much time that would take for them to roll this out. This trial, what we'll be doing is we're going to install EV infrastructure at the depot throughout London and the southeast of England. We'll implement something called a profiled connections that control the amount of network capacity used by each depot throughout the day. And then we're also going to use optimized charging in order to maintain that profile and reduce costs for the depot while ensuring vehicles are charged when they're needed. Next slide. Again. So this is just an example of some of the modeling that we've done. If you can click onto the next as well. Part of this project will also be designing a depot planning tool. So again, trying to simplify that process for the fleets, as well as helping the network operators in terms of being able to respond faster to requests for connections or quotes for connections. And this is looking at different inputs for the fleet operators so that they would understand what type of connection that they should be requesting based on their actual usage, based on any type of assets behind the meter solutions that they have that could have impact on that. Next slide. So we're talking about the profiled connection. Today, the current situation is, most of these organizations, they tend to base it on a worst case scenario. And if you look at a scenario where they're not using smart charging or they're not, optimizing that charge throughout the day to minimize what that capacity demand is. If you look at that red line, that's where the network headroom is. If you look at purple, that's kind of that connection capacity, and the green would be the demand for the EV. So this is an example of 100 EVs that are plugged in at one time. And, obviously when you go over that network headroom, that's potentially, millions of pounds of network upgrades that the fleet would have to pay. So if you go to the next slide. So what we're aiming to do with the depot optimization system and the profiled connections would be to look at how the fleets are actually utilizing their vehicles in terms of when they can charge and when is the most effective time or efficient time in terms of cost for them to charge and when there's capacity on the network. So this is really looking at two things. It's around, helping the fleet operators charge more efficiently, as well as ensuring they stay within the limits of that profiled connection. Next, please. So the other trial we'll be doing is with Centrica, with the British Gas fleets. And this is going to be for the charge at home. Centrica is the largest energy supplier in the UK. They operate the third largest fleet with about 12,000 commercial vehicles. Centrica will be providing data for vehicles charging as well as EV aggregation services for this trial. And next. So again, some of the challenges that we're going to be trying to solve for the networks and the fleets include the fact that networks right now, they really don't have visibility of commercial charging on the domestic connections and what impact a commercial load will have on that. So if you could imagine, in a world where, let's say, charging at a depot is too cost prohibitive for organizations, and if they decided to suddenly, have all their employees charge those vehicles at home, what kind of impact that could possibly have. And for the fleet operators, there's a complex process needed for employees to claim back charging costs. And another thing too is residential tariffs today, they're more expensive than what the commercial tariffs are. So with this trial, we're going to be looking at, monitoring charging of home-based commercial EVs to help understand the extent of the issues faced by the networks. We'll be trialing demand response to alter charging patterns when the grid is stressed. And they're also going to look at technical and economic solutions to make it easier to split that commercial and residential power usage. Next. So the third one is with Uber, a private hire mobility organization, and it's really looking kind of at that mixed fleet. So it's a combination of they could be charging vehicles at home, they could be largely relying on public infrastructure, where a lot of times that can also, if you look at charging hubs, almost act similar to what a depot would be. Next. And a key challenge for the networks and the operators is that they lack visibility of the potential demand for this really fast growing sector. And for the private operators, they need availability of charging infrastructure. So Uber's got some aggressive plans in terms of going purely EV in London. In order to do that, they need to make sure that the infrastructure is in place for their drivers to make that transition. The other thing is just understanding what that driver charging behavior is, where they're charging, why they're charging, and how they can help accommodate that better. So what this trial is going to do is collect anonymized data, the trip data from Uber's EVs across the Greater London area, and then we're going to combine that with the grid data to generate heat maps of charging demand and network capacity. So this is going to analyze, we'll basically looking at what that future demand is and the impacts of private hire or mobility operators, and also understand potential locations for where future infrastructure should be placed. Next. So in terms of the outcomes that we're expecting, the anticipated benefits of this program, for the UK alone, we're looking at about 2.7 million tons of CO2 by 2030, which is equivalent of a Boeing 747-400 flying around the world 1,484 times. In terms of the network capacity, it's a reduced overall load equivalent to about 1 million homes. I think the other key part here is we're also making this data openly available. So this isn't just about benefiting this project. We also want to have an impact on the wider ecosystem and other research projects, as well as other organizations that are looking to develop solutions to accelerate this transition. Next. So across the trials, and this is just some examples of some of the types of questions that we'll be answering in terms of, what are the usage profiles of commercial EVs? What's the impact with the weather, different events? Where can we make preemptive network upgrades? What are the charging hotspots in the city? And, kind of the impacts of state of charge and how it varies by time geography. And then also what incentives we could use in terms to change behavior, especially around things around flexibility. So just kind of in summary, again, we're really, in order to be able to do a project like this and to really understand what's needed, there's projects out there where you've got, very much a energy or distribution focus, or you've got ones that are very manufacturer, or very, fleet, where this one's actually taking a look at that entire ecosystem, that value chain, and bringing everyone together to understand what is that whole system view, what are the end-to-end impacts of these vehicles. And it's enabled by IoT, which enables us to, really overcome the challenges that come with, the different silos and, working with that data. So, and just very quickly too, can move to the next one. And this just gives you a view too in terms of, what this platform looks like, what kind of data that we're taking in, and also different elements in terms of, one to point out, we've got kind of this data innovation lab where we said we want to make this data openly available. So whether or not we invite, academics or other organizations in to be able to take a look at this data and, understand different types of solutions that we can also, or we could be looking at in addition to what this project's doing. If you skip to the next one. And this is, the different elements of the platform as well. So we've got the different data sources in terms of the partners being Uber, Centrica, Royal Mail, Scottish and Southern Electricity Networks, which I should point out, I apologize, I think I missed that in terms of the partners, is, this is with UK Power Networks, the lead network operator, as well as Scottish and Southern Electricity Network, and then our trial partners, Uber, Centrica, and Royal Mail, will be providing data for this project as well. And then looking at third-party weather feeds, and the charging data, and a number of different other, third-party sources that could also be things like, social media and looking at the impact events. So that's Optimized Prime. Thank you.
Okay, thank you.
Oh yeah, sorry. Thank you very much. And I hand over to Farah to pick out the main discussion. Sorry about the interruption.
Thank you so much to all for your presentations. I have been watching the questions coming in, which are great, and I would like to give the floor to the first question to Randolph Brazier from ENA UK. Randolph, if you go ahead and ask your question to the panelists.
Yeah, can you hear me?
Yes.
Great. So thanks everyone for the presentations. I've got a question for Urs on the German modeling example, and particularly around the comments that e-mobility can essentially fully finance the distribution grid costs till 2050. I was wondering what assumptions have been made around the existing grid, because we find in the UK a lot of that upgrade is not due to capacity, it's due to asset age and health. And also with EVs, we're finding that the pinch point actually happens with voltage and fault level before it happens with capacity. So capacity, doesn't always become the main driver for grid reinforcement. I was just wondering if he was able to comment on that. Cheers, and whether that had been included within the modelling. Thank you.
Thank you very much, Randolph. Very good questions. Maybe to the organizers, if you remute and mute, this will always lead to a short information to the speaker. So there's two parts actually. Fully finance the distribution grid expansion, and that the bottleneck is not always capacity, but voltage questions. I must say that this refers to technical aspects of the modeling, which our contractors actually did. So I can't answer that, to be honest. The idea of saying that EVs can fully finance the distribution grid expansion is that, of course, in the political debate, it is always said that EVs will cost all the electricity customers. And
so when we start with indirect electrification, the main topic of the second part today, it's clear that renewable hydrogen is the basis for a range of e-fuels. And the primary difference is that they come with or without carbon. Now, without carbon in the left part of the table is obviously hydrogen itself, but then also ammonia. And then you can move on to include carbon. And most important, probably methane, but you could also think about liquids like alcohols or hydrocarbons. And the big question is, what do we win and what do we lose with including carbon in those molecules? The absolute pro argument is obviously that they come with a very high energy density, and I'll get to that back in a second on the next slide. But the other argument in favor of carbon-containing molecules is that you might use the existing infrastructure for natural gas and liquids. The big counter-argument is you need more energy or you have higher conversion losses in production of carbon-containing molecules, and you need, in the long run at least, to find a sustainable carbon source. So that might be the air with direct air capture or some form of sustainable biomass, if you have it available. And another big con is methane as a particular molecule with a high global warming potential. As long as we continue to use methane, even though it might be attractive to use existing infrastructure for natural gas, methane always comes with a risk of leakage. And one very prominent example currently being discussed in Germany among, for example, the combined heat and power community is, well, for some gas motors, it's pretty difficult to kind of avoid this leakage. If you try to do so, you may have to invest so much and have kind of combustion after your real process that it turns out maybe too difficult and too costly to actually avoid and mitigate those leaking methane emissions. So that's a problem, and that shows that we should very carefully weigh the cost and benefits of including carbon into our molecules. Next slide, please. Now here, indirect electrification, nevertheless, is obviously very relevant for what's called the hard-to-abate sectors or segments in industry and the transport sector. And I just brought you this overview, which I found kind of nice, from the Energy Transitions Commission. I'm not going into details here. On the vertical axis, you see all sectors of the energy system, and on the horizontal axis, you see kind of a priority list. In the left part, you see direct electrification wherever it's possible, and then you see going to the middle and to the right, hydrogen, ammonia, and synfuels. Synfuels here means carbon-containing molecules. And so the question obviously is, what are the criteria for choosing a certain molecule as opposed to choosing direct electrification? And so it may have to do with energy density. That's very clear for aviation. It may have to do with high temperature heat, very clear for some industrial processes. But never forget that there is always, it's always good to ask, is there a direct electrification alternative And on my second slide, and I jumped over that, when you go back, when you download the slides, you'll see a reference to a big publication by engineers who came up with a lot of direct electrification alternatives for producing high temperature heat in industry. It has to do with induction, plasma, infrared, different forms of using electricity directly. And then obviously, final thought is when you need carbon, not for having a fuel, but for feedstock, obviously, and you see that in the right part, potential role as plastics feedstock. Obviously, the chemical industry producing plastics needs some molecular source where carbon is contained. And so this is kind of the overview for indirect electrification where we really need it. And then next slide, please. So the core of this is just to show you some of the figures when we talk about conversion losses. And here I brought you two examples for passenger cars and building heating to compare direct versus indirect electrification. Next slide, please. Now this is passenger cars first. You see three columns. To the left is battery electric vehicles, in the middle is fuel cell vehicles, and then the internal combustion engine vehicle. Now, all three start with the production of renewable power, so 100% in the upper part. Now, the more you move down, the more you have energy conversion, and you have energy conversion losses, and you end up with the lighter blue kind of total efficiency, over efficiency in all those three processes. And starting from 100% for BEVs, you end up with like nearly 70%, 69%. For fuel cell vehicles, you end up with 26%. And for the internal combustion engine used with a liquid that has been produced through a power to liquid process, you end up with a over efficiency of 13%. Now, this is the primary reasoning why it's a good idea to start with direct electrification wherever it's possible, because to travel the same distance, a combustion engine vehicle would need about 5 times as much renewable electricity as a battery-driven vehicle. And even for the fuel cell vehicle, it doesn't look that great compared to the battery electric vehicle. Now, obviously, there are other reasons and other considerations why you would maybe use a fuel cell vehicle, and I'm not going into details here, but just the conversion losses as the primary starting point for thinking about what is the best technology pathway should be a very strong argument in favor of this. Now, is this our own stuff? No. This is basically from a bunch of engineers from the German National Academy of Engineering, Architect, actually a bunch of professors who came up with this in 2017. We basically copied their figures. And this is obviously not about the exact figures. I'm not arguing about individual percentage points here. And if you're an expert in one or two of those processes, I mean, be my guest, you have more insight. The whole point here is that this is about the broad and big picture of comparing the three pathways. And yes, there will be innovation, there will be improvements in the future, but I would expect innovation and improvements in all three columns, maybe bringing up the over efficiencies, but still, it's unclear how the middle and the right column would kind of compensate for this distance to the battery electric vehicles anytime soon. Now, next slide, please. Similar idea, three columns, this time for building heating systems. And the title reads like, heat pumps have a particular leverage. Now, let's see. In the left part, we have heat pumps, electric heat pumps. In the middle, we have fuel cell heating, and to the right, we have gas condensing boilers. And same thing, you see that to the left, direct electric, alternative electric heat pumps, and this is an assumption of a coefficient of performance of like 3. And you see the factor between fuel cell heating, gas condensing boilers, and electric heat pumps is large, because more or less you yield 50% of your renewable power that you plugged into your fuel cell pathway or your power to gas methane pathway. Now, does that change in any way if we don't use fuel cell heating, but instead boilers with renewable hydrogen? I added here on the footnote, you see the Committee on Climate Change in the UK has published something on heating, and you see that they think you would end up with roughly 50 to 60% if you take renewable hydrogen and plug it into a boiler. that is not a fuel cell. So overall, heat pumps look so much better in this picture that we have to wonder, so what will be the counter arguments? And I'm getting to that in a second. Overall, heat pumps can also be used for cooling. And let me briefly acknowledge that, of course, you could think about using some of the waste heat in column 2 and 3 that is produced in the electrolysis process. But always ask yourself, is there heat demand, sufficient heat demand close to the electrolysis process? Because that's what you would need, maybe something like a heat grid or so. So a final slide, please. Overall, the question is how to make the most of PTX starts with asking, what does PTX include? And I think it really encompasses both direct and indirect electrification. And so if we go to indirect electrification through electrofuels, they will play an important role in decarbonizing chemical sector, industrial, think of high temperature heat, and parts of transport sector, think of aviation. But then if we talk about passenger cars, battery-driven electric vehicles are the energy efficiency benchmarks. For buildings, similar, heat pumps have a particular leverage, and therefore they also are the benchmark, and they can also be used for cooling. And then finally, this is all kind of conversion loss and energy efficiency considerations. Let me just say that this is definitely not the only criteria, but it's so strong that the open question for some applications from our perspective is, can those indisputable physics-based disadvantages of electrofuels be more than offset by avoidance of infrastructure cost? And that's in many respects, many areas, many regions, a very open question. And I think we need very good evidence to find solutions and find answers to that question. The question always is, who has the burden of proof to show this? Because the physics is pretty clear about the conversion losses. Thank you very much for your attention. One more slide is the one, it's just a reference to our study. Feel free to download it. There's a spreadsheet tool that comes with it, a presentation and a webinar itself, and you'll find it on the website, I guess, once we're done. Thank you very much, and my contact data is on the next slide.
Thank you very much, Matthias. If you could give me just a few moments, I will be queuing up the next presentation. Thank you. And for the next presentation, we actually have Jose Bermudez from the IEA speaking on the future of hydrogen. And I will give the mic to Jose. And please, as a reminder to all the audience, if you have questions regarding anything, please send them via the chat function. I, Farah, on the other side, will be looking through all of the questions and we'll be selecting 2 to 3 questions to open the floor to the audience at the end of this part. We see all of your questions, but due to time limits, we will limit it to 2 to 3 questions. Thank you for your understanding. And Jose, please go ahead.
Hi, good morning, everyone. Hope you can already hear me. I'm Jose Bermudez. I'm an energy technology analyst at the IEA, and I will be presenting today to you some of our findings from a report that we published last year called The Future of Hydrogen, doing some analysis on hydrogen technologies. Next slide, please. So with a global energy sector facing an unprecedented transformation, the versatility of hydrogen is attracting strong interest on a diverse range of stakeholders, including governments, electricity suppliers, electricity and gas suppliers, automakers, oil and gas companies. And the reason for that is that hydrogen can help in overcoming several challenges that the energy system is facing. It can help in integrating greater amounts of variable renewable energy, whose availability is not always well matched with demand. And it looks like a promising low-cost option for storing electricity over long periods, even for interseasonal storage. Hydrogen offers ways to decarbonize a range of sectors, including iron and steel, the chemical industry, or long-haul transport, where it is proving difficult to meaningfully reduce CO2 emissions, and it can also help in improving air quality impacts on those sectors. In addition, hydrogen can be produced from all fuels: renewable, nuclear, natural gas, fossil fuels, and it can not only be used directly, but it can be converted in other products like ammonia, synthetic methane, synthetic fuels, which is beneficial to improve energy security. However, everyone has seen previous false starts in the past for hydrogen. Within this time, it can be different if several key challenges can be overcome. First of all, that producing hydrogen today from low carbon energy is still costly. The development of the hydrogen infrastructures is slow and is holding back widespread adoption. Currently, it's almost entire supply from natural gas and coal, which has strong CO2 emissions implications. And there are some regulations around the world that are outdated and that are limiting the development of clean hydrogen industry. Next slide. We tend to talk about hydrogen as an actor for the future energy system, but it's already a huge industry, which is currently producing around 70 million tons of hydrogen every year, mainly for oil refining and chemical industry use. This is not trivial, since this amount of energy could power 50% of the cars that we have in the roads today across the world, which give us an idea of the size of this industry. And the demands of hydrogen are growing approximately at a rate of 3% every year. The problem is that almost all the hydrogen is produced from fossil fuels, which generates around 830 million tons of CO2 every year, which is equivalent to the whole emissions from the UK and Indonesia combined. There is a reason for that, which is easy to understand, which is economics. In most parts of the world, producing hydrogen from natural gas is the cheapest option, giving rise to prices between $1 and $2 per kilogram of hydrogen. This can be coupled with carbon capture and storage to reduce carbon emissions, although this is not taking place substantially because obviously there is a cost penalty. So approximately 0.5% of the pure hydrogen production today occurs through natural gas coupled with CCS. Producing hydrogen from coal is also cheap, this is a pathway that is mostly used in China. However, from the systems integration perspective, the interest lays on the use of electricity to produce hydrogen through electrolysis. This is clearly more expensive today, and scaled up is needed to bring down costs. In addition, we have to keep in mind that the source of electricity is key for the carbon footprint of the hydrogen produced. If in fact, in most of the cases today, using grid electricity does not save emissions when it is compared with hydrogen produced from conventional routes like natural gas. Next slide, please. As mentioned before, hydrogen is highly versatile and can be produced from many different sources and also transformed in many different products. This slide gives us an idea of how complex the value chain of hydrogen is. I would like you to focus on the graph on the right of the screen, which is where the electrolytic routes are described. Which, as I said, these are the most interesting ones from the system integration perspective. Through water electrolysis, we can produce hydrogen, which can be used directly as a fuel, or it can be transformed into ammonia through the Haber-Bosch process, or into a wide range of hydrocarbons like synthetic methane, diesel, jet fuel, methanol, through different chemical processes like methanation, methanol synthesis, or Fischer-Tropsch synthesis. Next slide. The electrolytic routes are costly, as I mentioned, but despite the cost challenges, scale up is happening for hydrogen production from electricity. Since 2000, we have seen over 200 projects started in operation around the world, and this is especially marked from 2010, when there was an acceleration in the numbers of projects deployed. Moreover, these projects are getting steadily bigger. For example, last month, the largest power-to-hydrogen project was inaugurated in Japan with a scale of 10 megawatts. And projects being announced today are as big as 100 or 200 megawatts compared to an average scale of around 1 megawatt in the last decade. Next slide. The operative management of electrolyzers also presents challenges. In grid electricity, electricity prices vary over time. We have low prices when there is little demand and there is a surplus of variable renewable energy generation, electricity generation, and high prices when demand is high and there is less variable renewable electricity available. Although very low or even zero electricity prices may appear as a very attractive way of producing hydrogen, these typically occur only for a few hours a year, resulting in low utilization of the electrolyzer and thus relatively high production cost due to the impact of CAPEX. With increasing load hours, the CAPEX contribution declines, but at the same time, the cost of electricity rises. Due to these opposing trends, a sweet spot, I mean, a point when we can achieve the lowest cost of hydrogen production can be identified. And in the example of the analysis that we performed last year, in this example, we can see this hotspot between 2,500 hours and 6,000 hours of operation, more or less. Next slide. However, even with optimized operation conditions, the price of electricity is and will remain as the main cost driver for electrolytic hydrogen competitiveness. From the analysis that we performed last year, it was determined that low electricity costs in the range of $10 to $40 per megawatt hour are required for electrolytic hydrogen to become competitive against the hydrogen produced from natural gas with CCS, when we consider a conventional range of natural gas prices. The introduction of carbon prices would enable competitiveness of electrolytic hydrogen with higher electricity prices, although the impact of CO2 penalties in the price of hydrogen from natural gas when it is coupled with CCUS is relatively low. Next slide. Scale up is also happening in projects for hydrogen production from renewable electricity, so with dedicated renewable electricity, although these projects are still mostly relying on government funding. The need to scale up is needed to become commercially viable. If so, we can see some remarkable opportunities around the world. From this geospatial analysis, we have found that costs as low as $2 per kilogram can be achieved in some regions in the long term, showing that hydrogen from renewables can become competitive with fossil fuels in certain situations in the future. Furthermore, the disparity on costs that we can see in this graph is remarkable, which can create clear opportunities for international trade, which is a backbone of a secure energy system. That means that some countries will have the opportunity to export renewable energy in the form of hydrogen or hydrogen-based fuels in a low-carbon global economy. Next slide. Now let's focus on some opportunities for hydrogen to contribute in systems integration. If we think about integrating variable renewable energy, we know that it requires flexible electricity systems, and this will require a large scale and long-term storage, especially in the future. Even more in particular in regions with strong seasonal patterns of renewable supply like Europe. Batteries attract a lot of attention these days. Lithium-ion batteries have the energy loss of a full storage cycle is very low, so efficiency is around 85%. Therefore, they are well suited for short-term storage and many storage cycles. If we think in long-term storage, the levelized cost of electricity storage increases since more storage volume is needed. In the case of hydrogen and ammonia, they have quite low efficiency or low cycle efficiencies, around 40%, resulting in very high cost for short-term storage. However, the cost for the storage volume are very low, so the cost when moving to long-term storage increases only slightly, making hydrogen and ammonia a lower cost option in this analysis for a storage duration lower than 2 days. Longer than 2 days, sorry. Next slide. In the case of power generation, hydrogen currently plays a negligible role. It's less than 0.2% of electricity generation. However, there is a potential for this to change in the future in areas like flexible electricity generation by using hydrogen-fired gas turbines or combined cycle gas turbines. The competitiveness of hydrogen-fired power plants when compared with natural gas-fired power plants for load balancing or for peak load generation depends completely on the gas and hydrogen prices and the potential level of carbon prices. In the example shown in this slide, we can see that with a 50% load factor and natural gas prices in the range around $7 per MBTU, and the CO2 price would have to achieve $100 per ton of CO2 to make hydrogen-fired power generation competitive with natural gas. Is if hydrogen price is around $1.5 per kilogram of hydrogen. If this price of hydrogen goes up to $2, the CO2 price needs to rise up to 175 tons per CO2. $175 per ton of CO2. So that gives an idea of how important the price of carbon price will be to make hydrogen generation of power through hydrogen competitive. Next slide. No, the next slide, please. Next one. That one. So finally, another alternative, which is regarding to hydrogen-derived products, synthetic hydrocarbons and ammonia offer an interesting opportunity to decarbonize certain transport modes like aviation and maritime, where hydrogen has limited applicability to its low volumetric energy density. However, the production of these fuels involves a complex value chain that comprises several processes, one after the other, and along this value chain, efficiency losses are accumulated, resulting in low overall energy efficiencies, will lead to high production costs. Next slide. In this slide, we can see a comparison of the current cost of several hydrogen-derived fuels, the potential for cost reduction in the long term, and the fossil fuels that these hydrogen-derived fuels aim to replace. We can see that as a consequence of the low overall efficiencies, there is a high impact of electricity costs in the final price of these hydrogen-derived fuels, and that it will remain so in the long term. Only in the case of ammonia, in the really long term, it could become competitive with conventional ammonia production. Next slide. Thinking about synthetic diesel or synthetic methane, a combination of both low electricity prices and high carbon penalties are needed, again, for making these fuels competitive. In this example, we can see that an electricity price of 40 megawatts hour per $40 per megawatt hour, a carbon price of more than $200 per ton of CO2 would be needed for making synthetic diesel to match price with conventional diesel, whereas more than $350 per ton of CO2 would be needed for matching prices with between synthetic methane and natural gas. Next slide. I would like just to finish with the 7 key recommendations that we identified in our report for scaling up hydrogen, which are establishing a role for hydrogen in long-term energy strategies, stimulate the commercial demand for clean hydrogen, especially in those sectors that are already demanding hydrogen, so trying to replace current demand with low carbon hydrogen. And address investment risk for first movers, because the first movers are going to face quite important costs that will involve a lot of risk. Support research and development to bring down costs. Eliminate unnecessary regulatory barriers and harmonize standards, which can actually be an enabler for hydrogen international trade. Engage international and track progress to identify lessons learned and best practices. And finally, focus on 4 key opportunities to further increase momentum over the next decade that we have identified as the use of existing infrastructures, the use of or making the best opportunities on industrial and port hubs, build on current demand, trying to replace demand of high carbon hydrogen with low carbon hydrogen. And finally, I would like to ask you to stay tuned for upcoming analysis from the IEA, since in June we will be launching our energy technology perspectives, and which will include an assessment of cost-effective technology choices to enhance security and reach net zero emissions, and then there will be some analysis also dedicated to hydrogen. And thank you very much for your attention, and I will be available for further questions during the QA session.
Thank you, Jose Miguel, for this very interesting presentation. I would myself, of course, have a question on expected transportation costs of hydrogen. You have shown very much spread regional costs of hydrogen production. But what about the transportation costs of hydrogen? I would be pleased if you could address this potentially later in the discussion once more. Now we have a little change in our agenda. Mr. Eaton unfortunately could not make it to the webinar, but he will be his spot will be taken by Mr. Rashidi from IRIS-10. He's the research director, and he will give us a short introduction of Power-to-X in Morocco. Well, Morocco comes up very often in the discussion as potential net exporter, not only of hydrogen, but also for ammonia, since Morocco has a well-established ammonia industry already. So I'm very interested to hear about the perspectives from Morocco. And Mr. Samir, the floor is yours, and please go ahead.
Thank you very much, Peter. Thank you very much for the organizers for the invitation. I'm really honored about this, and we are really happy to share with you the vision that we have about Power-to-X in Morocco in cooperation with some of the European countries, namely Germany. Next slide, please. So just 2 words about the IRIS-10, the Institute of Research on Solar Energy and New Energies. We are a research association or foundation created back in 2011, and we are chaired by the Ministry of Energy. We have two main missions. The first one is being a funding agency for our applied R&D projects. So we make periodic call for proposals for both academia and Moroccan industry concerning some issues on sustainability, technological issues or projects. The other role that we play is to develop or deploy some regional testing center or R&D centers dedicated to demonstration units and scale up projects, mainly to bridge the gap between the academia and the industry, so the intermediate TRLs for those who knows. Next slide, please. So this is a snapshot about the ongoing projects or research platform that we have already developed. So there are two platforms that are now operational. The first one is the Green Energy Park, and the second one is the Green and Smart Building Park. Both are in Ben Guerir, which is a small city near Marrakesh, for those who know. So those the first one is dedicated to applied research on solar energy, both photovoltaic and concentrated thermal. And the second platform is dedicated to energy efficiency in buildings, but also to smart grids and electric mobility. One of the projects that we are developing now is the green hydrogen and application platform, the green H2A, which is into the bottom of the slide, and I will be speaking about this platform in minutes. Next slide, please. So just a small outline about the presentation. I would like to give an idea about the regional context here in Morocco. What would be our vision, why Power-to-X now and why in Morocco? And also some words on the local context and what we are hoping in terms of socioeconomic impact. And I will finish by the next steps. Next slide, please. So next slide about the vision. So I wanted to start with this slide to remind some of you about this very ambitious initiative that happened like early in this decade or the past decade now, and the idea is that of Desertec was to export like green or solar electrons directly from the desert to the European countries. That was really ambitious, but and also positive vision, but it lacks a little bit, or it has faced some both technical and political problems, as you may know. But the idea that I want to highlight here is like now with this, and as the previous speaker has spoken about, we would like to review this vision of Desertec to another version, and that will be more inclusive for both countries that are on both parts of the Mediterranean, but also with more added value into the south of the Mediterranean. Next slide, please. So yeah, about the vision, we in Morocco, we would like hopefully in 10 years be one of the leading countries exporting high added value green or industrial molecules. We find this vision quite realistic because of the current situation or the urgency of the climate change. So we think that there is a very convenient context now for deploying this kind of, or this economy at larger scale. We have also very signals, very nice signals, or very consistent signals that Power-to-X is considered by many countries such as Germany or Netherlands as a very quick way to achieve zero emission targets. And then this will probably create positive conditions for the deployment of the international market. So since then, Morocco has a nice also renewable potential, as also shown by previous speakers. We would like to position ourselves as a key partner for people or for countries that would like to deploy or import PTX products. Next slide, please. So what about the local context? Here in one slide, a very quick and dense synthesis of what is the positive context in Morocco. As you may all know, we have high renewable potential both on solar and wind, especially to the south of Morocco. We have very nice wind spots that can be considered as one of the best in the world. In the last decade, we have also been able to deploy large-scale power plants, mainly CSP plants, and you may also have heard about the NOR program in Ouarzazate, and now in the second phase in Midland. We have a strong political support and international partnership with Europe, especially with Germany, with which we have a strategic partnership between Morocco and Germany in terms of energy called Barima program since 2012. In Morocco as well, in the last decade, we have seen growing interest for R&D and for all activities that targets growing or reinforcing the local capacity in Morocco, and in all those platform and initiatives that we have carried on as IRSN was also supported by the private sector or the local industry, mainly the OCP, which is the phosphate company that Peter was speaking about in minutes. We have also a strong proximity thanks to the geographical, let's say, situation of Morocco, and more than that, we are also connected with the gas grid to Europe via Spain. Next slide, please. So this is sort of the model that we would like to create to replace, let's say, the Desertec 1.0 model. So now developers of the Desertec are speaking about Desertec 3.0. So we would like to have a more inclusive European African Union in terms of energy. And we would like it to be also a vector of creating growth on both sides of the Mediterranean, with all what includes in terms of knowledge transfer, capacity building, employment reinforcement, but also the enhancement of infrastructure, creating a sustainable industry into the south, mainly via desalination plants, electrolyzer, and also chemical plants to produce PTX molecules. And I have cited here some actors, both Moroccan, mainly Moroccan, but there is the logo of Hanover, which is also a key partner for us since 2012 in the Green Energy Park, the first platform. We are collaborating on PV, and now we are collaborating with other 3 centers of Hanover on Power-to-X issues. Of course, there will be a need for support from IFIs, from cooperation agencies, and from also local governments. And as it was mentioned in a previous presentation, as we consider ourselves as first movers, we will need a lot of support, mainly financial support, to de-risk the investment in the first, let's say, pilot projects. I mean, even if we speak about 100 megawatts project, it's still a pilot project in the scale of Power-to-X, where we need gigawatt scale power plants or deployment. Next slide, please. So this was a very qualitative, let's say, even if we have some figures that illustrates the importance or the positive impact of the downstream of Power-to-X industry compared with only renewable power plants that may only export green electrons. And we have foreseen that for, let's say, we have, seen that for less investment and OPEX, less CAPEX and OPEX investment or efforts, we can generate much more labor, like sometimes up to 2 or 3 times the labor that we may have only in the renewable power plants. So this is why we believe that the power-to-X deployment of a power-to-X industry in Morocco may be also very positive in terms of socioeconomic impact with a country that is also that has a lot of youth in its demography. Next slide, please. Next, please. So now the first and next steps that were endeavored, and in here I would like to also highlight and the support of the German government via as I said, the PARIMA program, and also colleagues from the GIZ, the German Cooperation Agency, with which we have impulsed and carried out 2 preliminary studies back in 2018 that were shared internally here in Morocco with the stakeholders in 2019. One study was about the technology of power, the technologies that of power-to-X, and the other one is about the let's say the market or the economic potential of power-to-X economy here in Morocco. Those studies were presented back in 2019 in a workshop that gathers, as I said, all the stakeholders of the energy sector. And then the Minister of Energy that was chairing the session by that time decided to create a Power-to-X National Commission, which will then steer the activities that will be done for the Power-to-X in Morocco. And the minister decided as well to launch a further or a more in-depth study to produce a roadmap for Power-to-X in Morocco by 2040-2050. Next slide, please. So the first some first results of the study that was carried out by Fraunhofer Easy was estimating a little bit the capacity or the size of the market and what would be the opportunities for Morocco in terms of market share. And one of the most important, or let's say, outputs of this study, and of course some hypotheses, etc. Is that Morocco can capture up to 4% of the world demand on Power-to-X by 2030, which is quite a big figure, even if the share is small. But I mean, in terms of revenue, this is a very big figure for a country like Morocco. Next slide, please. And as Peter said as an introduction to my talk, we are a country that is also very focused on ammonia, because we are I think the first or the second exporter of phosphate-based fertilizers in the world, and but we don't have the ammonia in the country. Because we don't have gas, so we import OCP, mainly the phosphate fertilizer company imports all it needs from ammonia from abroad. Therefore, we I think by 2020 we will be importing around 2 million tons of ammonia, which is quite a big number. So the focus of ammonia in terms of Power-to-X in Morocco is both for let's say a pathway to decarbonize the fertilizer industry here in Morocco, to lower also the imports, because this is also money that is going abroad, and also in the future, why not to have green, or to suggest green fertilizers or green ammonia for countries that would like to have it in their energy or industrial mix as a feedstock. Next slide, please. So now we're speaking just very quickly about what IRESN do concretely in terms of preparing the way for a Power-to-X economy and industry in Morocco. Mainly, we are, as I said at the beginning, developing a platform dedicated to Power-to-X, so green hydrogen and application. Together with other partners like the University of Mohammed VI Polytechnique, OCP, and Fraunhofer. Next slide, please. So mainly the topics that will be tackled by this platform will be around hydrogen, because of course it's the key element to the rest of the Power-to-X downstream industry. Ammonia, of course, because of the reason I evoked before, and methanol can be also a very consistent point in terms of vector of or a precursor to power to L, PTL, power to liquids, which is also can find very, let's say, nice market issues in a lot of countries. Next slide, please. So yeah, in terms of TRL, those are details, but yeah, we would like to, as we have developed this platforms previously on the Fraunhofer model, I mean, to be a bridge gap between the academia in terms of TRL and also the industry. Next slide, please. So this is just to situate a little bit the project where it will be, the platform. We know, as I told you, of course, the main, let's say, potential is mainly to the south for the wind and PV. However, we have chosen a site that is the industrial site of OCP, which is one of the biggest chemical plants in terms of fertilizer production in the world. And the idea is also to be safe, to have an off-taker, and also for safety, because this chemical compound, I mean, manages, as I told you, around 2 million tons of ammonia per year. So they are really used to manage ammonia. This is why we would like it to be in the chemical plants. This will be also approximately be similar to the platform of Fraunhofer EMVS that is under developing now in the Leuna industrial complex near Leipzig, Halle. Next slide, please. So yeah, this is a small, let's say, description of the sites. The first pilot project will be in the yellow part, exactly within the complex. And the other advantages of this site is, as I told you, having one of the biggest chemical platform of phosphates. So then we can also have an off-taker. The chemical plant has a surplus of green electricity or carbon neutral electricity due to a combined cycle via sulfur exothermal process or combustion. There is also a very big industrial port there, so it can be also used to export the products, and also the site is near some CO2 sources like coal power plants in the region, and also a steel factory. Next slide, please. So yeah, this is the same slide, but just to speak about probably long-term or short-term scale-up perspective, because we are working under this. The first pilot will be around 5 megawatt capacity and up to 4 tons per day, 4 to 5 tons per day of ammonia, and the scale-up can happen in the same, let's say, within the same complex. And will be around 100 megawatts, and will use also the excess electricity produced on site. Next slide, please. Yeah, just to conclude, this National Commission had its third meeting on Monday. Yes, because of the COVID, we wanted to maintain anyway the meeting, and we made it online as well. And I wanted to share the main, let's say, outcomes of this meeting is that the three working groups will be created. One oriented towards the developments of a pilot project, bigger pilot project, probably around 100 of megawatts scale. The second group will be working on exporting opportunities, so developing this vision. And third, the group will be focusing on R&D efforts and demonstration activities. That was all from my side. Thank you very much. And yes, you will find my contact information. Thank you very much.
Samer, thank you very much for your presentation. And Germany was often mentioned, and from a German perspective, we can just emphasize on that Germany has a huge interest in getting ties to Morocco closer, since Morocco is the country we are expecting to could be able to access by pipeline transport potentially for importing hydrogen or whatever it's required. Other places around the world are quite far away for importing synthetic fuels. That's the reason why Germany is looking basically very much to Southeastern Europe and North Africa for its demands, and that's the reason why Germany is so much interested in the collaboration with Morocco. Now over to Farah for discussions and the questions that you have presented in the chat.
Thank you so much to all the presenters. Thank you, Frank. This is Farah here. We have received several very good questions. Given the time limits, we are looking to answer